Hi all, welcome to the second part of our tutorial. This tutorial is on advanced text representation methods for computational social science. It will be a hands-on tutorial, but you can also just follow along the presentation. If you want to reuse parts of the code in your projects or do the tutorial on your own, visit the GitHub repository and follow the installation instructions. This tutorial is part of Orion, a research measurement and knowledge discovery tool that enables you to monitor progress in science, visually explore the scientific landscape, and search for relevant publications. If you'd like to learn more about it, visit the links below or get in touch. So before I begin, let me say a few words about the team. So I'm Kostas. I'm a Mozilla Open Science Fellow and data scientist at Nesta. I work at the intersection of machine learning, economics, and policy. On Orion, I work with Zach, who is a creative technologist and data visualization engineer, and actually did the previous tutorial on Orion, and Lilia, who is a human-computer interaction researcher, interface designer, and digital artist. So the purpose of this tutorial is to show you how to transform textual data to vectors and use them in a variety of downstream tasks such as clustering, semantic similarity, and visualization. We will start with a collection of documents and transform them into vectors. Then we will use them in a semantic similarity task, where we will find similar documents based on an input. We will also visualize these vectors by using a dimensionality reduction method, and finally, we will apply clustering method. So I hope that by the end of the tutorial, you'll have a good understanding of the following: how to use transformers to create state-of-the-art representation of text data, how to build a Faiss index for efficient vector similarity search, how to use UMAP, a nonlinear dimensionality reduction technique, and how to cluster text vectors with HDBSCAN. And we'll do this by showcasing how Orion's vector-based search engine works and go through an example with real data, specifically academic publications on misinformation research. So to show you how things work and how they fit together in a tool, let's have a look at Orion's search engine. So with Orion, users can query the search engine by using a keyword or a longer text, for example, a sentence or a paragraph. If it is a keyword, we are performing a full text search on the title, abstract, and field of study of every paper using Elasticsearch and then return the relevant results. For longer queries, we encode them with a model that we will discuss shortly and then do an approximate nearest neighbor search using Faiss. Then we return the results to the user. So in this tutorial, we won't be explaining how Elasticsearch works, but if you're interested in learning more about it, let me know by opening an issue on our GitHub repository, and I will do either another video or write a blog about it. Okay, so let's begin. So in this tutorial, we will transform texts to vectors using a sentence-level Dilbert model. But firstly, let's do a very brief overview of how we ended up with that model by talking about some of its components. So the NLP community received massive attention around 7 years ago with the introduction of Word2Vec and a year later GloVe. So these methods could scale up to billions of documents and billions of words actually, and worked pretty well towards similarity and analogy tasks. However, they had an interesting limitation. Every word had a single vector representation. And that's a limitation since we know that a word can change meaning based on its content and its context. So for example, the word bank has a different meaning in the context of rivers and in the context of a robbery. So this problem was overcome by Elmo that created contextual embeddings. Another development that's relevant to the model that we will use is ULM-FIT, which made transfer learning, the process of transforming or actually transferring knowledge from one task to another, possibly in NLP. And then transformers and novel deep learning architecture proved that it's actually better than LSTMs at creating language models, while the OpenAI team developed a transformer that could be fine-tuned to downstream tasks. Then Google combined all of these developments and introduced some additional novelties and created BERT. BERT finds the vector representation of subwords, and there are quite a few versions of it. So one that's relevant to this tutorial is Dilbert, which is a much smaller and faster model. And another one that's relevant as well, but uses sentence-level embeddings. So why do you want to use transformers and BERT? So firstly, they are pre-trained models, meaning that we don't have to spend any resources to train them. Secondly, they are easy to use thanks to libraries like the transformers offered by Hugging Face. They also come with their own tokenizer, so we don't have to come up with any weird regex expressions. And they also offer better performance than previous models like Word2Vec. So final thing noting is that instead of using a sentence transformer, someone could also use BERT to produce sentence embeddings by one of the following methods. The first one is to average the embeddings of the last layer, and that's similar to averaging word vectors in Word2Vec. And the second one is to use the special CLS classification token to represent the sentence. However, literature has shown that both of these approaches might lead to low-quality embeddings and are usually worse than just averaging glob vectors. So with that in mind, I will go on with the sentence-level distilled model that we'll see in a bit. Okay, so with that out of the way, let's start coding. So we'll begin by importing the different modules we'll use. In this tutorial, we'll use a subset of publications on misinformation, disinformation, and fake news that were published between 2000 and 2020. The documents were retrieved from Microsoft Academic Graph using Orion's data pipeline. And we have done minimal data pre-processing and dropped any publications that were missing an abstract, title, or DOI. And here we actually show just a handful of columns: year, title, abstract, and paper ID. Okay, so first let's see how the data actually looks like. So overall, we have 5,500 publications, and let's store the abstracts in a list, just for convenience. So the sentence transformers library offers a variety of pre-trained models. So let's have actually a look at the spreadsheet with all the available models. Here, as you can see their names, and you can also see how they perform on particular tasks. So this one is, for instance, on semantic textual similarity. And you can see that in the distilled version we have different models. In our case, we will use the best performing one. This one has this particular name. So getting back to the tutorial, something that I should mention is that this is exactly the model that we are also using in Orion. So it's that simple to instantiate a model with the sentence transformer library. You just have to provide the string of its name. And encoding an abstract is actually really easy. So the instantiated model has a .encode method, which receives a list of texts, preprocesses them, and returns a list of dense vectors. And each vector will have a length of 768. So to confirm this, here is the shape of one of the vectors. Yes, it's exactly that. And the next thing that we could do is find the vector representation of all the abstracts. So I did this beforehand to save time, and as you can see, it took about 5.5 minutes. If you want, you can speed this up by using a free GPU with Colab. Cool. Now that we have the vectors, let's create a semantic search engine with them. So firstly, why do we want long text searches? I think that the first reason is that keyword searches are not very expressive. Searching with a longer text, such as a paper abstract or a blog, is more intuitive and something that links you directly from the source to the database. Moreover, how would you discover the unknown unknowns if you don't know the relevant keyword? So the longer text, it's easier to experiment with and come up with more relevant results. So, getting on to the method that we will use to develop the semantic search engine. So what is Faiss? Faiss is a library for efficient vector similarity search. It was developed by Facebook and scales up to billions of vectors given a GPU. However, in this tutorial, as well as in Orion, we use a CPU to run Faiss. So Faiss is built around the index object, which contains and sometimes preprocesses as well the searchable vectors. Faiss has a large collection of indices, and it's actually possible to combine some of them and create a composite indicator that should be performing better than any of these indices on its own. So with Faiss, you have to provide the dimensionality of the input vector, and it's important to note that Faiss uses only 32-bit floating point matrices, which means that you'll have to change the data type of your input before building the index with your data. So in this tutorial, we'll use an index flat L2 model. So this is a simple index that performs a brute force L2 distance search. It's actually very easy to use. However, it scales linearly. And for the purpose of this tutorial, it's going to be fine since we have only 5,000 vectors. But if you're working with more than 100,000, let's say, you should probably have a look at other methods that can speed up your index. So to create an index with the misinformation abstract vectors, we'll have to do the following. Firstly, as I mentioned before, change the data type of the abstract vectors to float 32, build the index and pass it the dimension of the vectors it will operate on, then pass the index to another object called index ID map, which enables us to provide a custom list of IDs for the indexed vectors. And finally, add the abstract vectors and their ID mapping to the index. And in this tutorial, we will be mapping vectors to their paper IDs that are coming from MAG. So let's run these 4 steps. Okay. So now, as we can see, our index has the same number of papers in it as the abstract vector, so everything seems to have worked all right. Okay, so to search the index, Faiss will do a k-nearest neighbor search, and we have to provide the number of neighbors to be returned. So let's query the index with an abstract from the misinformation dataset and retrieve the 10 most relevant documents. And the first one must be our query, right? Because that should be that must be actually the most relevant. So I chose this paper that it is titled Detecting Fake News in Social Media Networks, and it has an abstract that talks about fake news, social media, hoaxes, and more. And we can actually use the .search method to search our index. It returns 2 objects. So the first one is a list with the distance between our query and the top 10 results. And as we observe, the distance from the first vector is 0, which means that we retrieved the paper that we queried. So our index works well. And the second object is a list with the paper IDs we provided earlier on. So using a utility function I created, we can actually see the titles of the top 10 results. Indeed, the first one is the paper that we queried, while the rest of them seem to be relevant. For example, many results mention fake news, fake online content, and other relevant things. And actually, this seems quite useful. However, so far, we've built a Faiss index using the misinformation abstracts when encoded with a sentence-level Distilbert model. However, that's not helpful in a real-world scenario where we would have to work with unseen data. So to query the index with an unseen paper, let's say, or an unseen abstract and retrieve the most relevant documents, we would have to do the following. Firstly, we will have to encode the query with the same sentence Distilbert model we used for the rest of the abstract vectors, change its data type to float 32, and lastly, search the index with the encoded query. So let's grab the first paragraph of this commentary published in Harvard's Misinformation Review, and let's see how it looks like. Okay, so I grabbed this paragraph over here, and we see that it talks about COVID, health-related things, and of course, it is on misinformation. And I assigned it to a variable just for convenience. And actually, we can see that the top 10 results, and we can search, and then we can see that the top 10 results seem to be relevant to the unseen query, so our index seems to be working well. So we can find a lot of things related to COVID-19, for instance, or other medical things. So yeah, so that's cool. So now we know how to build a Faiss index and perform semantic searches by utilizing the sentence level Distilbert embeddings we created previously. And I should note that instead of using the Distilbert model, you could actually use Faiss with other vector representations, for example, with TF-IDF vectors. Moving on, let's say how to use UMAP for dimensionality reduction. So UMAP constructs a high-dimensional graph representation of the data, then optimizes a low-dimensional graph to be as structurally similar as possible. And in that sense, it's quite similar to t-SNE, which might be a more familiar method. So let me zoom out a bit. So UMAP has some notable hyperparameters that you have to experiment with. So firstly, it's the number of nearest neighbors, which controls how UMAP balances local versus global structure in the data. So low values give you local structure, larger values focus more on global structure. The second hyperparameter is the minimum distance, which controls how tightly UMAP is allowed to pack points together. Low values lead to clumpier embeddings, might be good for clustering. Larger values focus more on the global structure. The third one is the number of components, which is identical to what you might know from scikit-learn and methods like PCA, and controls the dimensions of the low-dimensional projection. So if we want to visualize this, this would be 2 or 3D. And lastly, the metric controls how distance is computed in UMAP. Okay, so why UMAP and not t-SNE? Mainly for two reasons. UMAP is faster and creates a more accurate low-dimensional representation. And actually, I would highly recommend you reading this blog to learn more about UMAP and its differences with t-SNE. And we have actually used the methods that we have described so far in Orion. So for instance, we have transformed papers to vectors using the model that I used before. And we have projected them into a searchable 3D scatter plot using UMAP and Faiss. So this is all very relevant, and could actually be used, right away to your projects as well. So to project getting back to the tutorial, to project the dense abstract vectors to a low-dimensional space, we'll have to do the following. So firstly, instantiate UMAP with a set of hyperparameters. As I said before, in order to find the right one, you have to experiment a lot with it. Then we have to transform the abstract vectors, and finally, in this tutorial, we will visualize them with alter. And note that you can get deterministic results by using a random state. Okay, so let's instantiate UMAP and project the abstracts to a 2D space. So UMAP is running now, and should complete fairly shortly. And we can see that it has the same length as the number of abstract vectors, and 2, because that's the dimensions that we gave to it. Okay, so let me refresh this and zoom out a bit. So now that we created a data frame with the UMAP embeddings and also added a column with the paper titles, we can see 3 distinct groups, one here, a second one over here, and then some papers over here as well. So let's explore them a bit further. Okay. So they seem that at least this cluster over here seem to be non-English papers. So what I would propose is let's focus on the main cluster over here for the purpose of this tutorial by removing all papers with a component 1 that's lower than 0. And of course, treating them like this is rather crude, but it's fine for now. So let's redraw the scatter plot and explore the neighborhoods. Okay, so as you can see here, that That's much clearer. So let's explore some of the neighborhoods actually. So starting with this one over here, okay, this seems to be about Russia and disinformation and elections. Let's explore another one. So, okay, so this seems to be more about children and misinformation around children and preschool. Another one. Okay, interesting. So this one has a lot of papers on Indonesia and misinformation around it. Cool. So it seems that, yeah, UMAP works well actually. So for the last part of the tutorial, let's cluster this two-dimensional space using HDBSCAN, and then let's explore it again. So instead of clustering the 768 dimensional dense vectors that we created with the sentence level Distilbert model, we will use the UMAP embeddings as a pre-processing step. So this is a bit controversial, as UMAP does not completely preserve the points density. So using it as a pre-processing step might produce an inaccurate number of clusters. So, and there's actually a really good discussion on Stack Overflow about this particular issue. So bottom line is it might work, do a few sanity checks before reporting any results. So here we'll use HDBSCAN, which is a density-based clustering, and we'll do the following. Firstly, we'll instantiate the HDBSCAN model and choose the hyperparameters. Again, as with UMAP, you have to experiment a bit with it. Secondly, we'll predict a label for each vector, and thirdly, we will plot the results. So UMAP has, so HDBSCAN has some notable hyperparameters. The first one is the minimum cluster size, which controls the smallest size grouping that you wish to consider as a cluster. And the second one is the minimum sample size, which controls how conservative you want your clustering to be. So let's fit the HDBSCAN. Let's fit our data to the HDBSCAN. So note that HDBSCAN produces an additional label, -1, for the points it considers to be outliers. So in this case, we have 33 different clusters, excluding the outliers. And finally, let's plot the results. Okay, so it looks like, so our data looks like this. So let's focus on some of the clusters. So for instance, let's go onto this cluster over here. Okay, so this one seems to be more about methods and the different methods and machine learning methods in particular that have been used in misinformation. Cool. Previously, I think that we explored this cluster over here. Yeah, this cluster. So another one, let's go this one over here. Okay, so this one seems to be about climate change, atmospheric science, pollution, and climate change. So yeah, this seems to be about climate change. And let's explore a final one. Let's go to this area over here. Okay, so this seems to be about age and HIV in South Africa. So yeah, it seems that most of the clusters work quite well. And actually, if we wanted to just choose the outliers, it seems that it are these highlighted points. Cool. Okay, so in this tutorial, we covered a lot of ground. So we saw how to transform text to vectors without spending time on pre-processing the documents. We developed a semantic search model by building a Faiss index and adding the dense vectors to it. We reduced the dimensionality of the document vectors using UMAP and used HDBSCAN to cluster them. And some other things that you could actually try is to fine-tune the sentence Distilbert embeddings to your dataset. You could also fit multiple UMAP models and choose the one with the most suitable representation. You could also try another fuzzy clustering method or k-means instead of HDBSCAN. So overall, I hope that you enjoyed the tutorial. Get in touch if you have any other questions or if you would like to learn more about Orion. Thank you.